So it's going to be on image processing. And it's from Pravish, Pravish Senath, who's our learning and project an AI project lead. He's a PhD student at Mila, University of Montreal, in brain-inspired AI, machine learning for neuroimaging. And previously he was at Hammerhead, which is a New York City based tech startup, in which he was building software for Byte computers. Thank you so much, Pravish. Do we have Pravish?
Thank you very much, Sim, for the Thank you very much, Sim, for the introduction. Let me share my screen. So I'm going to share a Colab URL on the chat, and this we'll continue from tutorial from last week. I hope it's visible.
Yes.
Okay, perfect. So I'm going to share the Colab link. Okay, so last week we just looked at the basic ideas behind computer vision, and we started exploring OpenCV, which is a framework to apply these ideas using code. And just to recap, OpenCV is just a library of functions which supports many of these image processing operations. And it was initially started by some developers in the open source community, and later acquired by Intel. And there are other alternate libraries such as scikit-learn and Pillow that you can use, but we'll look at OpenCV. But no matter which library you get to use, the ideas are going to remain the same. It's only the syntax and ways of doing certain things that might change, but the idea is going to remain the same. And we run the first cell, the installation. This is normally the OpenCV Python package is by default installed by the Google Colab environment, so it doesn't really have to install anything, so it's already satisfied. So these are a couple of imports to support some interactive features, and like open import CV2. This is the only import that is required for OpenCV, and everything else is accessible through CV2. Just to have an idea, all the underlying functions are implemented using C++, and the Python is just like an upper layer which transmits these function calls and achieves it through faster computations using C++.
And Pravish, could you just zoom in a bit?
Zoom in. Oh yeah, sure. Yeah.
Thank you.
Okay. I hope it's okay. So this is just an idea about the version that you need that is installed, but in most cases you would not need any specific version, but when you work with other libraries, there might be some compatibility issues, and so the first thing which we ran last time, but which is necessary to run, is this cell. It just downloads some sample images from like a public repository. Okay, it's disconnecting for some reason. Okay, I'm just going to reload. But in the meantime, this is going to download some sample images, and we're going to work with that. And last week, we mainly saw operations to read, write, and display images. This week, and we saw some basic ideas of some image transformations and filtering. We'll look at that again briefly, and then our main focus for today would be object detection, how to detect different kinds of objects in the image, and we'll end up landing on segmentation using a commonly used algorithm which is implemented in OpenCV. Okay, I'm just running these import cells again, and this clone. So once you run this clone, you will see, if you click on this directory button, that you would see there will be like a sample imgs directory folder, which we see here, and this contains a lot of these images which you can click to view, which we'll use in our examples. Okay, so these are the list of images. So we saw the read and write of images, which I'm not getting into now. If it's unfamiliar, you can just run these cells. It's pretty direct, or you can watch last week's video. So the basic idea we saw was a notion of color spaces, where an image can be represented in different color spaces, which are essentially these color channels, which combine the pixel intensities to produce the actual, like the true colors of the image. And we saw RGB, grayscale, and this is binary image, which is 0 or 255, only two values possible. And here is the three channels, R, G, and B, with values, integer values from 0 to 255 possible, and grayscale image with just one channel with integer values of 0 to 255 possible, which are shades of gray between white and black. And here, binary image, you can associate these with black and white, but this is just a color space, yellow and purple, just for reference, which is shown. Okay, we saw some basic operations with like a thresholding operation, with just thresholds, like sets a certain threshold for images and detects the significant features. You can see here that the outlines or the illuminations of these fruits have been detected. There is like a fixed threshold. Anything above 127 is black, and anything white, and anything below is black. And the other way around, this is called the inverse threshold we saw last week. And there's this adaptive threshold to let the algorithms figure out themselves what is the threshold to fix. And then there's one more method called OTSU method, which if you're interested, you can read about it online. It's like all of this is math, but it just identifies like thresholds these images, it binarizes images into black and white, so we can detect some features. So yeah, we saw about inverting color spaces and resizing images, which is very useful when you have a data set with images of different sizes and you need to uniformly modify them. And then we saw flipping and rotating images. This is an interactive cell. You can select the angle and you can run the interactive cell. This will show you the image, the original image and the rotated image based on the angle that you select here. And the only operation here that we use is cv2.get rotational matrix, where you specify the image center. Image center is nothing but the midpoint of the image, and along the rows and columns, like this point, maybe, yeah, it's 500. The image size is 512, so it's around somewhere around 256. So here it's somewhere around here. Okay, and yeah, we get the rotation matrix based on this angle and the midpoint, and then we apply the rotational matrix using what we call an affine transformation, and we just get the output image and we plot it. Okay, and we saw about cropping images. You might need to, when you have images with a lot of background information that is not necessary, you might need to crop these images to focus on what you need. And here, this is an example of reading the image, and like these are the index values of the area, like the ROI, the region of interest, and you just need to pass that, and you get like if you were there in the previous tutorial on data manipulation, this is just array indexing. So you see here that the tank is in between 150 and 300 roughly. So it's 150, 300 along the rows and 150, 300 along the columns. And you can see here that that is what matters in your image, and you just select the index values. And finally, the cropped image is what you need, and it has a reduced size. You can see it's no longer 512 times 400 something, it's lesser. So the number of pixels is reduced. And there are some logical operations on images which are possible, like arithmetic and logical operations. Arithmetic operations to add two images, subtract images, multiply and divide using some fixed values. Okay, I don't know why it's taking more time today, but okay. Okay, let me share another screen. I have a backup screen. Okay, I think it's visible right now. Okay, I'm just going to quickly run to the cell in which we were there. Okay, so we're looking at arithmetic and logical operations. Yep. So you just select the operation, like add, and you just add some value to specific pixels, and you can see that adding values, in this example, if you look at the code, you're just adding you're just adding it to the image, which means this is called a broadcast operation. So the parameter that you select here is just a value which is added to every pixel out there. So you can select the operation, like subtract will dim down the pixel. I mean, it increases the contrast and so on. You can explore that. And similarly, logical operations like bitwise operations, which you would have seen, but let's get to, yeah. You're just doing these logical operations with a certain mask. Like you can see, there's a darker patch, there's a gray patch, there's a white patch, and R just, if there is a pixel, it just does some bitwise R operations of pixels in the original image and the mask. And you can see the same thing with the AND operation. It's AND is like a multiplication operation, right? So it just darkens this whole column, and then so you can explore that. Okay, so we saw about histogram, like representing images as histograms of pixel values, and how you can enhance images, the enhancement that we see in our filters and our camera applications. They essentially do this kind of change in distribution of the pixels. Okay, so now let's go to the place where, okay, yeah, this is an illustration of the filtering operation, which is going to be the basis for everything that we do today. And you can see here in the figure, in this idea, there is this image which is shown here in blue. The white outline outside is called a padding, which is used in many cases because as like extra buffer space outside the image, so that you can apply certain operations uniformly. If you look at the case here, so you can see here that there's like a 9 grid matrix or 9 grid cell, like 3 rows and 3 columns, that is being slided along, and then in the next row and so on, if you look at the operation. So this is what we call as the kernel or the filter. And a filtering is just an operation of applying a certain kernel or a filter on an image which has optional padding. So if you see the operation that's being applied, along the corners or even along the borders, you can see here that the number of pixels is lesser than what you can expect in somewhere in this middle of the image. You can see there all the 9 pixels are inside the image, but in the corner, if any operation is applied with just these 4 pixels, then they get like an unequal weightage of the operation. So padding is just to make that uniform. So this is the output image, the filtered image that is the result of the filtering operation. So any filtering operation need to ask 2 questions. What is the filter, like the values on this filter? And second thing is on what, like, do you have to do something to the input image before you can apply this filter? Because for certain operations, it's necessary that the images are in grayscale, are in binary, or are thresholded, or like there are some prerequisites for the filters to actually make sense and to actually extract good features, detect good features. So we might need to ask that question. So there is a question. Are there specific cases in which each pre-processing RGB binary grayscale offers an advantage over the others, or should I focus on the algorithm performance, choose any of them? Yeah, for certain standard algorithms, there are some results from how others have applied it in their projects, where grayscale is preferable for certain operations and features to detect, and in some cases they're not. And in some cases, especially in the deep learning context, what we do these days is we apply something called the random transform. Like, you have images which are mostly in RGB, in full color, and then you randomly sample some images and you augment your data set with like images transformed to grayscale, images transformed to binary, perhaps, just to make your neural networks learn from like a diverse set of images, so that the features which are distinct in all of these transformations actually may make sense for the algorithm. So to answer your question, for certain most commonly used algorithms, it's in the non-deep learning context. there are some results which you can make use of to decide. And in the deep learning context, in most cases, we use what I just explained, like augment your data with as many transformations of the image as possible. Next question is, what is the result of each square? The mean of the squares in the CNN. Okay, so this, the result of each square, you can see here that the filtering operation is essentially like a multiplication. So each of these 3 times 3, which is shown here. So the kernel has certain values, and as it's slided along the image, the values in the image and the which are essentially pixel intensities represented by the image, which we saw last week, and the values in the kernel are like multiplied one over the other. So whichever cell of the kernel is superposed on the cell of the image, the values represented by them are multiplied. For example, let's choose, when it comes here, like, yeah, 60, like this cell from 60 till 70 here, so it's 3 times 3. So 60 times 0 plus 113 times minus 1 plus 56 times 0 plus 73 times minus 1, and so on till 99 times minus 1 plus 70 times 0, right? And the value is computed and placed here. So whether it's the mean or a median or anything, it really depends on the kernel. So if I actually choose the kernel to be all ones, then it's called a mean filter, because if you just apply not just one, it's like 1 over 9. If I select each value of the kernel to be 1 over 9, because there are 9 cells, then the operation, the filtering operation, is called a mean filter operation, because it's 1 over 9 multiplied by all these values, essentially adds these values and divides these by 9, which is actually the mean of each. This is what we call as the patch. So each kernel is applied on a patch of the image, and you do like a pixel to pixel multiplication on the patch, and you add them all and put them in your output image. So why the kernel is, next question is why the kernel is 0 minus. But this is just some kernel, which I'll just show you how the choice of values in the kernel really determines the operation, and you'll get an idea. But you have a lot of references done by the image processing community to really understand what these values mean. Essentially, you can see here that the middle pixel is of the highest value, and you can imagine this to be like a mountain which has a peak in the middle, and it is like, it has like all these pits across. So this is to really detect point features. So it detects point features, like point features which are like pixel values which are higher in its own patch. For example, in this case, yeah, here 131 is the peak among all the other of 8 of his neighbors. Like all the other neighbors are lesser than 131. So it really is sensitive in detection of these pixel values over, say, something else like the lower value pixels like 70. So visually, this will give you some difference in what features are observed, but we'll see some examples here. Okay, so the first type of filters are like different kinds of spatial filters, and these are linear. So what I just explained is a linear operation, because you just multiply the values in the kernel with the values in the patch and add them all together and put them in the result. So we're going to look at filters which like the choice of the mechanism, the setup of the filtering is in such a way that the input and the output images have the same dimensions. So it's essentially like applying a filter on your like the filter that you apply on your photos on your that you click with your mobile phone. So we look at something called the box filter, which is actually a blur operation, and then we look at different kinds of blurs based on, when you look at it visually, you will try to relate it. But you can read more about the theory if you're interested and if you have an appetite for that. So this line, the apply, oops, okay. It's just taking the image that I stored in the ing variable last. So I'm just gonna, yeah, I'm just gonna switch it back to this image. Hmm. Okay, okay, but in the meantime, let me just explain what to expect here. Okay, or even in this image, you can see what is essentially being done. It's a blur filter. You can see that the coins here are like super blurred on this one. And if you just look at the code, cv2.blur, it just you just have to select the kernel length, which is selected here to be 5. So when it does this operation, but it has like the patch size, which is the same as the kernel size, is 5 pixels times 5 pixels, and it applies this blurring. Again, it is the blurring operation is associated with a certain value of the kernel, which is known by OpenCV in this case. And then Gaussian blur it uses values based on like the Gaussian distribution. And then median blur, it just replaces every patch, so every patch like this with the median value, median, which median in this sense is the mean median mode median, which we use in statistics. The median value of all the values in the patch is replaced for all the values in the patch. So that's what makes the operation blurry. And like again, bilateral filter, it just uses like a kernel of twice the length and does the same thing. I'm not getting into the details, but this is just to illustrate a simple idea of filtering. And you can see the blur operations here, okay? And next is about, okay, it's still executing. It's, okay, let's just continue. Okay, the next category of filters, what we saw so far are like linear and spatial filters, because these are spatial operations. Every operation is inside a patch and it's related to its neighbors. And other filters are like Laplacian filters, and these are motion filters. Again, I'm not running the cell in the interest of time because we need to look at the main object detection part. But the original image, you can see that when you apply a certain filter for motion, which is just like replacing 1/2 of the filter with ones and the other half as zeros. So in this setup, like it's like replacing 1/2, the left half with zeros and the right half with ones, or the bottom half with zeros and the top half with ones. And you apply that filter, it kind of simulates a motion. So you can see that the original image is this, and a horizontal motion filter applied image. You can see it's a little bit shaky, and it seems like the camera has been moved horizontally. And you can do the same. You can change the option here to V and run it, and you can see it's a 10 length kernel. You can see, and if you keep changing the length of this kernel, you can see different motion effects. And as we can go from like a stable image to a motion filter image, we can even go the other direction. And some basic cameras detect like help fix motion motion stability issues in the picture based on this. Okay, and again, I'm not getting into details of this one. This is called morphological. Next category is called morphological transformations. Morphological, morph means shapes. So these are transformations for the shapes. And theoretically, you can read about this in this link. Theoretically, these are applied on binary images because that's where the notion of shape is like pretty simple, as opposed to color images where shapes could mean different things. Like there's this notion of illumination and so many other things. Okay, so maybe I'll just show here this example also. So there are different kinds of operations, but the basic operation is called, one is erosion, other one is dilation. And erosion, as the word itself indicates, if you start with this image, you're just eroding away. So white is supposed to indicate like some object, some useful content, and black is supposed to indicate background. And erosion is an operation which tries to thin down the content, the white, and dilation, you can see from this J to this J, it is eroded. The white has actually thinned down. And dilation is an operation which does the opposite. It dilation, as the word itself indicates, like erosion, it's the opposite, where it tries to like blurrily expand the content. You can see the J gets thicker as it gets here. So this is useful in really highlighting and identifying certain useful artifacts in the image. I welcome you to play with different kinds of these words from the if categories here, and you can see the result. And so dilation and erosion are the basic operations, and then we have other operations such as opening, closing, gradient, and all that. So opening is just, and all of these are combinations of these two operations of erosion and dilation, and the set operations like union, intersection, and complementation operations, which is complementation is replacing black with white and white with black and so on. So opening, it just opening basically discretizes the objects as much as possible, and it neglects objects which are like which are supposed to be nice from its perspective. And closing is the opposite operation, where the nice inside the useful content, which is the white, is removed, and so on. And you can read about the other operations here. I'm not going into them in the interest of time. And in this specific example, you can see here, this is an image of a cell, and it's pretty noisy because of the recording. And you can see these white blobs are the cells, and these other noisy characteristics are emerging from something which is unnecessary. And once you apply the opening operation, you can see that the discrete cells are recovered from this. Okay. And this next category of operations is affine transformations, which are translation, rotation, and scaling operations. You have other operations such as shear, which is demonstrated here, which are combinations of the operations I just described. And here again, as we saw in the previous case of rotation, we have to identify a transformation matrix, which you can do by selecting a set of source points. And like, so you can see the source points are 0, 0. Cols minus 1 is the last column. So the last column, 0. The 0 rows minus 1 is the first column, last row. So these 3 points are selected. So you can see that this point here, and this point here are selected, and those are transformed to different locations. Like we want the initial top left point to remain in the same position, so 0, 0 remains 0, 0, and the top right, which is the cols minus 1, 0, to really remain, go to half the column, like here. And then the last row, like the bottom left point to actually transform to the middle here. So you can see that this wall is now sheared. It's now shifted to the, so you can see the point 0, 0 remains here, and this point comes here, and this point actually comes here. And this is now transformed the image into a different stretch. So this might be essential in operations such as this, which is called like perspective transformation. If you want to select this, these are some UNO cards, and if you want to really focus on just this card, and you have to select the points and apply the transformation. And that gives you a matrix, this matrix, which you can apply to the other images, other parts of the image, and like normalize them. This is very useful when you have a data set which is raw. You may need to apply these as pre-processing steps to really focus on content which is required. Okay, so now let's quickly look at like detection operations. So as I said, all these detection operations are going to be filtering operations, and some. So this answers your questions, Simon, about what that filter does. This, if you see, is like it has like a peak in the middle, and it has -1 elsewhere. And this is a typical point detector. You just type in this kernel, and you apply the kernel using the CV2.filter to the operation. This is IMG, which is the source image that you read from this path, and kernel. And this -1, if you actually look at the documentation here, it's source, ddepth, and kernel. And ddepth is just the depth. Putting -1 there only indicates that retain the depth from the input image. Don't do anything with it. So this is different from the -1 you saw in array context. -1 here in like these kinds of function calls really indicates that retain whatever is in the input, don't change it. So that's it. And this is just plotting. So it's just determining this matrix and displaying the result. That's all we're going to do in the next couple of cells. And you can see after running this cell that the input, this is the input of some cells, and these are the detected points. So the detected points, like after applying the point detection transformation, you can see that they're whitened. The like those pixels, which are like the peak pixels in their patch neighborhoods, are like whiten more. So this is like a simple point detection operation. You can change these values with different proportions, and you can see the result. And then there's this line detection, which again has a certain filter. So all that we're going to care about in the next couple of cells is just what is this filter. So you can see here that like point detection had -1 in, so -1 basically indicates I don't care, and higher positive values means I care. And this filter is supposed to be like a template for what you're looking for in the image, and it applies this template using the filtering operation, and the output image is supposed to indicate what you want. So again, if I'm looking for horizontal lines, then I want like the row or the row above the line to be something else, and the row below the line to be something else, and the line to actually be like a continuous stretch of pixels. So this is how it is. So it's -1 in the first row, -1 in the last row, and the middle row should be 2, 2, 2, or it can be 8, 8, 8, or any high positive value. And similarly, it's the transpose of that, which is the vertical. It's a rotation of that, which is the vertical filter. So applying that, we see that in this case, the input is like an array of bricks, and you can see applying the vertical filter, you can see that the vertical lines are highlighted. Okay. So that's it. So and then the next category are filters. These are simple point and line filters. And the next category of filters are some specialized filters which can detect edges which are more complex edges beyond just points or lines. And you can play and change and play with this. These use more advanced algorithms which use a combination of point and line detection and kind of combine them iteratively in some manner. Examples are Sobel and Canny filters, which are commonly used. And this is an example of a Canny filter. So this detects, if you see here, this detects the outline, the silhouette of the image. And this is useful in many applications such as segmentation and others. This is not perfect. You can see the gaps here, but you can keep changing the type of filter and the parameters, and you can see how this goes. But this is just a starter code for you to, again, if you see, like different methods require different values. So Canny and Sobel are simple filters which just require certain parameters of the length and width of the kernel and so on. And other more advanced filters such as pre-width and edge detect require you to specify the kernel directly, which are given here. Okay, and so you can play with that and you can ask questions based on that. Next is the hue transform, which has like a line detector and a circle detector. And again, you can see the example here for a circle detector. Again, it requires a certain input, which is like median blur, and then a Canny edge detection needs to be applied, and then Canny edge detected image needs to be passed to the hue circle detector, and these circles are acquired here, and these are plotted or like overlaid on the image just for viewing. So you need to be careful about the kernel that you're applying or the technique of algorithm, technique which of detection that you're applying, and if it needs to be like blurred in some manner, if it needs to be grayscaled and other inputs. For example, in this hue case, it needs to be Canny filtered first. Okay, you can see that the circles are perfect. So this is another example of detection based on color instead of the shape. So this filter basically selects the green skittles, because we call the function using green. So detect color objects, detect the green skittles from this image, and these are just markers which are approximately laid on the green skittles. This green here, we just give the lower and the upper range of the green color in the RGB space, and then it compute an image mask in the HSV transformed color space, because it's easier to detect these in the anything related to color. HSV really works well, and given the HSV image and the lower and the green upper range, you get the image mask, and you apply the image mask on the raw image, and you get the output image with just the green skittles highlighted. Okay, and then shape detection is again based on a function called approximate polygon detection. So you pass the image to threshold it. This is a prerequisite for this, and then pass the contours from the thresholding to a polygon detection algorithm. And depending on the length of the number of points in the polygon, you classify them into triangles, rectangles, and circles, which you see here that they've been correctly classified. So this is the final example, and we'll end here. So this is for a full image segmentation pipeline, and we see here this is the source image, which is a set of coins. And our target here is to actually do some kind of instance segmentation, which means it's not just sufficient for us to identify that there are kinds, like which pixels contain kinds, but also really distinguish between the different kinds. Okay, so the first step. So for this, we're going to make use of some algorithm called the watershed algorithm. The reference links are given, which is very commonly used in image processing. And we just read the image first, which is kinds.jpg. And the grayscale, we convert it into a grayscale image because it's easier for many of these thresholding and segmentation algorithms, because the color is not essentially a very useful feature here because they're all almost the same color. And there's a clear distinction in the background with respect to like a simple grayscale shade. Okay, so run this, and then we just plot, and we apply the OTSU thresholding algorithm because we're going to take this. It's like a pipeline. We start from the color image, we convert it to grayscale, we apply the OTSU thresholding algorithm, and it kind of gives us a notion of what like a foreground and background features. And then the next, what we do is we use the thresholded algorithm to apply, we kind of denice it using the morphological transform, which is an opening transform. And we use the opening transform to denice it because you can see here that it almost recovers the shapes, but like still the kinds are like stuck together, and it's going to be difficult to identify the kinds when these boundaries are blurry. So we remove the noise, and then as we identify some kind of a background area, like a shear background, by dilating it, and we compute some kind of a foreground area by applying what is called as a distance transform on the opening image, like a noise removed image, and we get a foreground area. And we get some unknown area, which is like a subtraction of foreground and background. You can see here that opening transform image, it smoothens these edges, and it's a little bit better than the previous one. And the background, you can see that the black is the far sheer background. We're sure about the background, that the black here is background. And the foreground here is the white small blobs here, which we are sure is the foreground. And finally, we apply like a function called connected components on the foreground to really mark these areas which we detected. So finally, after these steps, this is just to show that like how unique are the markers. It detects 25 components actually, which are 24 kinds and one for the background. So there are 24 foreground components and one background component. And finally, you apply the watershed algorithm on these detected markers. I'm not getting into the specifics in the interest of time, but there's a tutorial on OpenCV's website, which I recommend that you look at and pose your questions. And finally, after applying the watershed algorithm and plotting the markers, you can see here that the edges, the boundaries are now way better. Although they're not perfect, there are some like kinks here and there, but these are better than before because the watershed algorithm. Okay, so I think I've answered all your questions as and when they came, but if you have any final questions, I'm happy to answer before wrapping up. I think we're over time.
Yeah, thanks so much, Pravish.